learning and editing. So we also tackle various challenges from learning disentangled representations to learning without labels. So her research outcomes have been published in top venues, both computer vision and graphics. So she received her bachelor in CS from Peking University. Her work experience includes research internships, Google, Uber, Meta, and Microsoft. So let's welcome Sami.
Hi, thank you everyone for your patience and for coming to my talk today. So today I'm going to present some of my recent work along the line of learning to edit 3D objects and scenes. We are immersed in a very fascinating 3D world. In this 3D world, we have many individual objects like chairs, bottles. Sorry, it's the animation's not working. Oh.
So after shift we count.
Yes, they suddenly closed.
Okay.
So we have many individual static objects and also many computer objects like drawers and doors and closets. I'm interested in the early aspects of the 3D world, including individual objects and the entire scene. Around this 3D world, there are many interesting topics, and there are three in the center. One is recognition, the second is reconstruction, and based on the 3 R's of computer vision by Professor Jatendra Malik, there is also another circle called reorganization. And in my context, I will call it 3D editing. Maybe you're more familiar with the first two circles that tries to solve what the world is, and the third circle tries to solve what the world could be. My past research has been really about all different problems with around the three circles. But today, I'm mostly going to focus on the circle on the top right and talking about 3 of my recent works. 3D editing is very important. So please stay with me. So I think the first 2 videos should also be moving, but they're not moving now. So 3D editing is very important in many applications, from AR, VR, industrial art design to robotics. For example, in this robotics application, you should imagine where the door will be after it's open, so that you can plan what's your next reaction. So how to edit 3D object and scenes? Let's look at 2 examples, and then after these 2 examples, you will find the answer. The first example, professionals may have been using tools like Blender to solve very complicated 3D editing operations. For example, if our goal is to lift the character's arm, people might use software like Blender to do a very complicated vertex by vertex operation. If we imagine all the possible 3D editing in the high-dimensional space, and then the operation enabled by Blender is actually the arbitrary points in the geometric space, which may be very time-consuming and have limited scalability. For example, in this case, if our goal is just to lift the human body's arm, and if we have a semantic understanding of where the human arm is, then we can easily perform the operation. So in this case, if we have a semantically meaningful space, meaning here pose, or a well-structured space for a human body, then we can have more efficient and better operation, also with better scalability. Another extreme is some people have been using like cages to deform the deformation. For example, in this 2 representative work, they use a 40-vertex spherical cage to guide the deformation of the 3D mesh. However, operations provided by those cages are too constrained in the very low dimensional geometric space, and therefore can only support very coarse control. If the dimension can be a little bit much higher, then we can have a much more semantically meaningful space and then can perform more precise control over the 3D shape. So after looking at these two examples, my answer towards editing 3D objects and scenes is to exploit the underlying structure. But how? This task is not without challenges. The first challenge is, although we have many big scale 3D datasets like for 3D reconstruction, 3D understanding, but there are no datasets with labels for 3D editing existing. The second challenge is, for example, from this observation of the laptop, we're going to maybe try to learn the articulation or learn the appearance. But in this observation, from this observation, all the different properties like geometry, texture, semantics, articulation, they are all highly entangled. So how are we going to disentangle some properties that we are interested in is also another challenge. The third challenge comes from the fact that in many cases, although we want to edit 3D models, but we only have partial observations available, like only RGB images or only depth images. With all these challenges, the three projects that I'm going to talk about today will try to solve one or some of these three challenges. So with all these challenges, I'm going to talk about three of my recent work trying to solve one or some of these three challenges. The first work is about editing semantic attributes. And in this task, we don't have access to label 3D data. And in the second work, I'm going to talk about how to edit object articulation. And in this task, we are faced with highly entangled properties and partial observations available. And in the third task of scene editing, I'm also going to talk about the strategies that we're going to use to exploit the structure with unlabeled datasets and highly entangled properties. So for the first work, learning to infer semantic parameters for 3D shape editing. In this task, as you can see here, our end goal is given any 3D model, we can use a simple tool like a slider to easily change one attribute of the 3D model. For example, here the attribute is the thickness of the chair back. So what did people do before this project? People might use software like Blender to do this. They first select the region and then stretch the chair back, and then they got artifacts. So the shortcomings of this current pipeline is First of all, they need to manually give the selection. There's no semantic understanding of the tool. And second, after the operation, the detail and topology may be changed. Thirdly, they cannot achieve independent part control. For example, although in this case, they want to add the chair back, they may also have changed the chair seat, which is not wanted. So our goal is to try to overcome all these three shortcomings. There have been lots of prior work in this field. The template fitting methods, they are not scalable, they are very sensitive to initialization. And then because we don't have enough data set, so data hungry methods that requires supervision is not suitable here. And thirdly, for some deep learning based work, sometimes they will have support only coarse editing. Sometimes the result will lack semantics or lose details. So how does our framework look like? Given an input shape as on the left, the yellow shape, our goal is to make the chair back thinner with the desired shape on the right. To achieve this, our framework is composed of two steps. First is semantic shape encoding, the second is deformation transfer. We first encode the shape attributes into latent space, and we perform the editing in the latent space, and then decode it back to some synthetic shape. The difference between the synthetic shape can define the deformation field that can guide the deformation of any arbitrary input 3D shapes. I want to note that our framework is very different from autoencoder, because for the traditional autoencoder, they encode the entire shape into the latent space. Because latent space always has limited dimensionality, meaning there tend to be some loss of the details. And also they can only support very coarse control. In contrast, we don't encode the entire shape, but we only encode the semantic attributes that we are interested in the latent space. So the attributes only corresponds to the deformation field, and then we can leave all the input geometric details untouched. Therefore, we can preserve details and achieve effective control. There are two challenges in this task. The first challenge is how to specify semantic parameters, and second is how to learn without label realistic examples. For the first challenge, as you remember, there's no label dataset existing. So our solution is to leverage user-defined template. But the user-defined template is very easy to define here. Within a few minutes, we can use 6 boxes to define the chair. And for human bodies, we don't even to define it. We can use existing simple parameters. And we also want to note here, although you may ask, this chair has 4 legs. Would it work for chairs with 1 or 3 legs? The answer is yes. So later, I will also show some generalization with the current framework. The second challenge is how to learn without labeled realistic examples. The answer is we can leverage the synthetic data that we just created. So for the synthetic data, we encode it into this attribute space where each dimension of the attribute corresponds to some attributes that we are interested to edit. And then we decode these 2 attributes into the synthetic data. Because they are synthetic, we have perfect labels for all the shapes. We can have perfect reconstruction loss. And then we're going to encode realistic data within the same latent space. But here we decode it into another synthetic shape. Because here we don't have the ground truth, we will have a similarity loss between the synthetic output and our realistic input. Both of the realistic shapes and synthetic shapes are trained together so that we learn the latent space that can distill the knowledge learned from synthetic data to better infer the real data. So let's first look at some results of the semantic encoding and decoding. For example, for this realistic shape, our synthetic estimate looks like this. It seems we have estimated the key attributes of the semantic parts, and we can estimate this for every different input shapes. And after this synthetic estimation, we can perform many interesting applications. For the first application specifies anisotropic scaling, meaning given a shape, we're going to use the slider to drive the animation of editing a part of the chair. For example, for this chair, we can easily perform this isolated piecewise isotropic scaling for different part of the chair without changing the details or changing the other parts of the shape. We can also, here we compare with a prior work called dual SDF, which uses a deep SDF inspired structure to encode the entire shape into latent space. And we can note here, where shapes has many details, those kind of frameworks tend to lose some of the details during the auto encoding and decoding process. So, and also our framework is able to perform different editing operations like making the seat depth higher, making the leg higher, making the seat width bigger. With all these operations, we are able to preserve all the details while performing the desired operation. And we also do this on airplanes. And here again, DUSDF tends to already lose some details in the reconstruction. And while trying to modeling the different attributes of the wings, fuselage, and the stabilizers, our method is able to better preserve the details while performing the desired operation. We also tested it on the out-of-distribution toilet, where although we are trained on templates with 4 legs, we're still able to perform different editing tasks for chairs that are out of the training distribution. Here, the human body is also out of distribution because we train it on simple shapes, but here we tested on shapes with hair and also complicated pose. We are able to perform editing of individual poses. Another interesting task is source to target deformation, where the goal is like here. So we have 2 shapes. Top is the source shape, bottom is the target shape. Our goal is to deform the source shape so that we preserve all the surface details of the source shape, but from the structure side, it looks like the target shape. To do so, we also do the encoding and decoding using the deformation defined by the semantic output to guide the deformation of the source shape. We compare this with another prior work called neural cages. Remember, neural cages are using the cage of 40 vertex sphere to guide the deformation. And with this, they can easily create artifacts and cannot preserve all the details, like preserve the angles. But our work is able to preserve all the angles. And we also do this source target deformation on this out-of-distribution skeleton. While neural cages can only perform very coarse editing and therefore causing all the artifacts, our method is able to preserve, for example, the size of the skeleton while performing this post editing. A final application is now we can scan a realistic source shape and using the target shape from simple parameters to generate an animation. So without any registration, we're able to animate this realistic source scan data. And these are 2 views for this animation. So in this first work, to exploit the underlying structure, we use semantic data that has all the non-semantic structure. However, in this case, we assume we have access to 3D data. What if we don't have access to 3D data? In this work, I'm going to talk about how we are going to leverage disentangled representation to separate structure. This work is called self-supervised neural articulated shape and appearance models. So the end goal is here. I can use my iPhone to capture multi-view images of my laptop. And here, all the laptops, they have the same angle between the screen and the keyboard. In other words, they have the same articulation status. Our goal is, using my framework, I can easily create an animation with both appearance and the geometry for this static laptop. You probably are familiar with many great work in this field for reconstructing static objects, from earlier work that used 3D supervision to more recent work like nerves using 2D supervision only. But in this project, we are more interested in reconstructing articulated objects. For this topic, so for articulated objects, there have been first line of work, they try to use, try to reconstruct human bodies and animal bodies. And I know there have been lots of seminal works from labs at NTU working on how to reconstruct or better model human bodies. And most of those work, they could not work really well for general objects. And another work before this project was called ASDF, where A stands for articulation, and they use 3D supervision for both shapes and articulation to train this model. However, if they only have RGB images available, those work probably cannot work very well. At this point, you probably can think of nerve extensions by trying to use some nerve models to train on dynamic scenes. But those work, typically, they train a single nerve to work on a single scene. Given a new scene, you need to retrain a whole entirely new model. So they cannot reuse the same model to work on a category of different objects. So our goal is the opposite. We want to model general objects from only RGB images on a category level of different objects. There are a few challenges. The first challenge we're already very familiar. So from this image of the laptop, there are all different visual properties tightly entangled. And we need to separate what is geometry, what is articulation, what is texture. The second challenge comes from articulation. So first of all, in this project, we assume we don't have any ground truth articulation. All we have are all these post multi-view images. And also, we don't want to design a model that specifically works on a single joint type. We want our model to be flexible enough that can work well on different joint types. So here's a brief view of our method. We first designed this learnable latent embedding space where for each object, we explicitly use 3 parts of latent codes to model it, including shape, appearance, and articulation. During one forward pass, we first predict the geometry using the latent articulation code and latent shape code. And given this geometry and given another camera view, we are able to use those information together with appearance code to descriptively render the image. And the difference between the predicted image and the ground truth image can give us a loss signal to be backpropagated and update the model. So here are the 3 points that I want to note. The first is latent articulation. So the green part, the green code is not any explicit angle like 60 degree, 90 degree. It's all randomly initialized before training and then optimized throughout the training process. And secondly, there is a forced disentanglement. You may wonder here, before the geometry MRP, the articulation code and shape code may seem may seemingly same, but we can force disentanglement through the following operation, method. So for example, for the same laptop, they have 2 articulation status, and then we will force this, when generating these 2 images, we will force they reuse the same shape code and appearance code and the 2 MRPs. So the differences reflected in the image can only go back to the articulation code. That is how we enforce disentanglement. And thirdly, we also, different from nerve, we also incorporate categorical prior, meaning for another laptop, they will share the same MRP. So the 2 MRPs, they have encoded the priors from laptop category, and then the object-specific information is encoded in 3 latent codes. So we have trained and tested our model on shaping the currently largest dataset for articulated objects on 1 revolute joint, 2 revolute joint, and joints with a combined prismatic and revolute joint types. Here are more results. Let's first look at results on reconstructing semantic test shapes. I'm going to show you many videos. I hope the PowerPoint will not crash again. So the first column is the ground truth appearance. Second column is our appearance. We can see we can pretty much reconstruct the most details of the appearance. And then third column is our geometry. Fourth column is the geometry from ASDF. Sorry, I'm going to show many video clips.
Yes. Oh. Yep. 。
Sorry,
对，因为我发我微信上，对，你直接发我微信可以。
我登一下你公众号，那个我只帮这回事。 for your patience. And so here I've already shown you the first two columns of the appearance. The third and fourth column is the geometry comparing our method and ASDF method. And we can see, for example, the doors of ASDFs, they may get holes, while our method is able to have much smoother results. And we also compare on this more challenging eyeglasses where it has very thin structures. And still, we are able to pretty much reconstruct both the geometry and appearance. And we can see the ASDF glasses, the legs get broken, and the front shape does not match the ground truth. And last example is this closet with joint type. It has both the door and drawer. And we can see from here, our method is able to produce, again, much smoother articulation throughout the animation. And the ASDF doors, sometimes they have intermittent holes. So another quick experiment is the interpolation and extrapolation. So given us two inputs with two articulation status, and we will going to optimize and get the code and then do the interpolation. And we can see, so here it's supposed to be a video. So we are supposed to see that throughout articulation, the base and top of the stapler from ASDF does not conform with the ground truth input. And this exploration is also supposed to be a video, but it's the static again. So we're supposed to say, but even from the static frame, we are able to notice the difference between the ASDF output and ground truth, where our shape is much closer to the ground truth shape. And expression from another side. So lastly is reconstruction animating static real objects, as we've already seen in the first slide of this project. And I've taken multiple images of my laptop. And then using my pre-trained framework, we can use those images to do backpropagation to update the three latent codes. And after this backpropagation, at this point, we are already able to reconstruct the appearance and shape of the static laptop. To make it animatable, we need to use some more articulation codes. To do this, we can replace this single articulation code with any articulation code from any trained laptop. And then we are able to make a video out of it. So you've probably seen the video in like 10 slides ago. So this is supposed to be a video, but now it's static. So you can imagine a moving laptop yourself in your mind. And we have more results, more interactive results, and also stable video output from our website if you're more interested in looking at more examples. So here, now we have talked about two examples on how to edit single objects. The last project is how to edit the entire scene. And in this task, our goal is to remove the clutter objects out of the scene. We call it clutter detection removal in 3D scenes with view consistent intending. So now imagine you're doing a summer internship and you want to sublease your apartment. But instead of taking a few pictures and upload the pictures online, you can now use your iPhone to capture both the RGB video of your room and then reconstruct the 3D mesh and upload the mesh to the website. So people can move the mesh around to see whether they're interested in your apartment or not. But now in this room, there are many clutter objects. By clutter, we mean all those frequently moving objects like backpacks, chairs, pillows, books that typically moved in many days. Maybe, for example, my bedroom is very messy. I don't want people to see this messy room, so I want to clear all these things up. Also, clearing the clutter objects is very helpful for example, for reconstructing from videos of moving objects. So, how to edit the scene such that you can remove all the clutter and create this clutter-free scene? This task is composed of two steps. The first is clutter segmentation. The second is 3D imprinting. For clutter segmentation, the goal here is different from traditional segmentation, where here we want to segment across objects of shared properties. And for 3D imprinting, you're probably very familiar with 2D imprinting. But for 3D imprinting, you need to imprint with both coherent geometry and coherent texture. So the end goal is, given the 3D input mesh with clutter, we are going to output the 3D infinite mesh without clutter. For the first step, clutter is very challenging clutter segmentation is very challenging because first of all, clutter is very ambiguous. For example, the board is one of the categories provided by existing dataset like ScanNet. Board sometimes can be installed on the wall and therefore non-cluttered, and can also sometimes be portable little whiteboard and therefore cluttered. Also, clutter objects mostly have very low quality annotation. For example, in this scene, some of these white regions are unlabeled, and like this little pink dots on the tables are mislabeled as non-cluttered table. It is also challenging because it is very heterogeneous. The x-axis plots all the clutter categories within ScanNet, and the y-axis is the number of instances per category. We can see all these blue categories are the categories that have less than 20 instances per category. For example, within all these 1,500 scenes, there are 3 sponge, 2 backlogs, and 1 fish. And most importantly, clutter objects are typically small tail objects. For example, in this scene, all the random objects on the tables are small objects. And if you train this segmentation task with traditional cross-entropy loss, you will find this loss is driven by mostly detecting the bigger objects. And for smaller objects, they will just miss it because it does not make much difference in the final performance. So we instead propose arithmetic loss by adding a weight. Here, the denominator of the weight is number of objects, not number of points of the object. Basically, the idea is if the object is quite small, then the number of points of object is also smaller, meaning the denominator is smaller, Wi is bigger, and the loss signal is bigger. Then this is how we are going to better segment the smaller object. And we want to know this is not class imbalance loss, because our loss is on the instance level, regardless of the class. And here is the K that controls the strength of the weight. And more specifically, when K equals to 0, when K is bigger, Wi is bigger, meaning the loss strength for a smaller object is bigger. And when K is equal to 0, this entire weight equals to 1, and this goes back to the normal cross-entropy loss. Here's a tiny ablation study on this arithmetic loss. On the left is the input mesh. In the middle is the clutter segmentation without arithmetic loss. In other term, is using the cross-entropy loss. And we can see these yellow parts are the missing parts. And with the arithmetic loss, we're able to better segment the smaller objects and also the boundaries of bigger objects. You may see here all the false positive, the pink parts in the red result. But this is actually good for our task because for the purpose of indenting, we can not only segment the exact object, because the object also casts shadows and change the lighting conditions around the object. So if we want to do a better indenting, you probably also want to remove all the shadows associated with the object so that it will not indent something bad later on. So after the 3D segmentation, then how to do 3D indenting? The biggest challenge is for this 3D indenting, if we do this directly in 3D, all the semantics and geometries are highly entangled. You can easily create artifacts here. So our approach is to leverage 2D because we have great, fantastic 2D indenters already. So we're going to disentangle the semantics and geometry in 2D. And more specifically, we will first project the 3D into RGB and depth and do separate RGB and depth indenting so that we can then reconstruct the 3D scene. And in more detail, we first leverage the existing pre-trained image indenters to this indented RGB image, and then we can use the RGB to guide the completion of the depth model. And after this step, you can do this for each of the different views. And at this point, we are still not yet ready to reconstruct an entire scene because the 2D indenters result may be very view inconsistent. For example, here, the first image is the mask RGB image with the mask on the clutter. And the inventor may return us with this image in the second row of a bigger table. You can imagine sometimes in this view, the table is bigger, in some other views, the table is not bigger. So if you reconstruct from here, you will have this very messy reconstruction. Therefore, we further propose view consistency multi and pruning and do it iteratively to remove all this view inconsistent artifacts and make it view consistent. And after this step, we are ready to reconstruct the mesh and have 3D imprinted mesh. Here is the full pipeline results on ScanNet dataset. The first two images are the texture and geometry of the input mesh. In the red circles, we can see all the proper objects. And then a third image is our segmentation results. From the segmentation, the first two images in the second row is our imprinted texture and geometry. And then we compare with Poisson surface reconstruction in the third column and the whole filling algorithm from MeshLab. We can see for Poisson surface reconstruction, this reconstruction algorithm cannot fill in the holes that already exist in the RGB image. And even if we run whole filling algorithms, because whole filling, they are very sensitive to what are the hole size that they are going to fill. So sometimes they're missing big holes, and even for smaller holes, you can see the artifacts, those oversimplified surface, and you can easily notice that they are not original surface. We do this comparison in many different scenes from ScanNet, and we can see from all these different scene types, we are able to better fill in the texture and geometry compared to Poisson surface reconstruction and whole filling algorithm. And now we all have a deeper look at the imprinting results, and we compare. We do this comparison on Metaphor 3D datasets. The first two rows, there's supposed to be a video so that you can see the actual 3D, not this static. So the first two rows are the input with holes and the ground truths. And we can see our method is able to better fill in the holes because the 2D imprinter already has the semantic understanding. So they know this is the sofa, and then they can fill in the hole of the sofa. And we compare with two prior work. They use a very heavy 3D convolution to do this imprinting prediction on the TSDF volumes. We can see they are outputting results with lower resolution and also cannot fill the hole. And here is another video comparison of the matte imprinting. And again, we can see that we can imprint back with the coherent texture and geometry. So here is pretty much the top, like the content of the three prior work. And if you're going to leave maybe after this talk, I hope you may remember not only the delays and all the crashes of the videos, but also some takeaways. So first is extracting the underlying structure is very critical for 3D editing. More specifically, when no label is available. From the first work we learned we can leverage synthetic data with no structure, or from the second work we learned we can force disentangle representation that separates structure. And then when noisy labels are available, we can design better losses that better learn with noisy labels. And although I have these are all three works from me doing 3D editing, but I can imagine there are many different exciting topics within this field, and there are many open opportunities. First of all is the generalization. So like in all this my three work, sometimes they cannot work very well on real data. Sometimes they cannot work on other categories. So generalization tools on scene categories and real data are always a very important task that we want to solve. And also more diverse and flexible 3D modeling tasks. For example, you can try to, like I have been working on modeling, editing 3D objects, but what if we want to have more complicated editing tasks in the entire scene, or even how can we edit the dynamic object or dynamic scene? Like I've already seen, for example, this year S3E4, they have been work that uses NERD to do this 3D editing. And I can imagine with all this development of the new 3D representations, we are able to do more flexible editing tasks. So towards these two challenges, maybe one solution is to use always build bigger datasets and then train on this bigger dataset for 3D editing models. For example, there have been work like Omni Object 3D from this lab and Objectverse XL, and I believe they are excellent works, and we're still very hungry for this 3D data, and I believe there are even more work on this direction. And also there's another direction of improving the algorithms. So for example, for generalization, you can try to find built-in physical models to add stronger regularization within the model. Or, for example, the second work we use disentanglement. So maybe there are also better disentanglement strategy to help with the regularization in the latent space to help with generalization. Or we can even use text image models pre-trained on large-scale datasets so that we can leverage the prior knowledge distilled from the language side to better guide the generalization of 3D modeling, although we don't have enough 3D dataset. And for more diverse and flexible editing tasks, one way is to use the 3D generative models so that we are able to generate more data to train better 3D editing models. And towards 3D generation, there have been lots of work on this task, especially in the past 1 or 2 years. For example, for static 3D generations, there have been works like Dreamfields, Dreamfusion, Magic 3D, and also other works that try to solve, following those works that try to solve some specific issues within this domain. Like some works, they try to solve the lighting surface materials, some they try to overcome the oversaturation or low diversity, or for example, work Jim Gaussian from the lab that tries to strike a balance between speed and performance. And I'm even more interested in dynamic 3D generation. I think this is going to emerge in the coming months or years. And there are lots of issues to be solved within this topic. First is the efficiency and consistency. So the biggest difference between dynamic scenes and static scenes is the temporal consistency. And I believe maybe with the current development from for example, 3D Gaussian splatting and so on, we are able to find algorithms that can have higher efficiency with better consistency. And also for dynamic scenes, current algorithms, I think there are lots of redundancies across many domains, across many axes. For example, there are redundancies across time, redundancies across objects with shared properties, or for different things, there may have some similar microstructures that we may leverage to better reduce the redundancy and improve the efficiency. And here, in the fourth bullet point, just some imagined task. For example, to better generate images with shared, for example, we can generate images with shared contents to learn priors. For example, if we want to model dynamic squirrels and we don't have a dataset for squirrel, so we can leverage current image generation tools to generate all different squirrel moving around, like squirrel eating a nut, squirrel running, or squirrel climbing a tree. And then using these images, we can design some neural 3D representation that learned that can be learned across the different squirrel data. And then so the shared embeddings will be able to learn this core features for squirrel, while still and then we use some separate features to learn the different details of different squirrel images. And so this is one of the possible directions that we can leverage the 2D generative model to better learn dynamic 3D. But this is just a very naive way, but I can imagine there are many more exciting works coming from modeling dynamic scenes. So yes, I'll end my talk here. I hope you can bear with all this unexpected accident. And if you have any questions of my project or in this field in general, I'm happy to take any questions. Thank you.